All right, today we're going to go deep, I mean microscopically deep, into something you see every single day: cement. Now, I know what you're thinking. It's just boring gray powder, right? Well, it turns out it's hiding this incredible world of chemical superstars that are the real reason it has its strength. Let's get into it. Seriously, think about it. We are surrounded by these absolute giants made of concrete. Towering buildings, massive bridges, you name it. But what is that invisible magic that lets a wet, soupy mix turn into something strong enough to, literally hold up our entire world? Well, the answer isn't magic at all. It's chemistry. The incredible strength of concrete comes down to a carefully balanced team of four main compounds. You should really think of them as a tiny construction crew where each member has a totally unique personality and a very specific job to do. So, come on, let's pull back the curtain. It's time to meet these four secret ingredients that pretty much make all of modern construction possible. Now, these four compounds are all born in the same place: the fiery heart of a cement kiln, inside something called cement clinker. Just picture that as the raw, super hot ingredient that gets ground down into the fine powder we know as cement. And our four superstars? They fall into two main families. Okay, so if you look at the clinker, it's mostly dominated by one group, the silicates. They make up about 80% of the whole thing. The other 20%, that's the aluminates. Our four players are split right down the middle between these two groups, two in each. Let's start with the real heavy lifters of the bunch, the silicates. The silicates are, without a doubt, the absolute backbone of concrete's strength. I mean, these are the guys responsible for how hard the concrete gets and, this is crucial, how fast it gets there. This is our strength squad. So meet C3S and C2S. And honestly, the best way to think about them is as a sprinter and a marathon runner. C3S is our sprinter. It reacts with lightning speed, giving concrete most of its strength in just the first few days and weeks. But then you have C2S, our marathon runner. It's a slow, steady worker adding strength over months, years, even decades. And that little analogy, it totally explains this number. In modern cement, the sprinter, C3S, makes up about half of the entire mix. And why is that? Well, because in today's fast-paced construction world, we need buildings to get strong, and get strong fast. That huge demand for early strength is exactly why C3S is the star of the show. So what's the secret to their different speeds? Well, it all comes down to their crystal structure. I want you to imagine C3S as a jumbled, messy pile of Lego bricks. It has all these exposed surfaces and corners where water can get in and start a reaction. That's why it's so fast. C2S, on the other hand, is like a perfectly stacked, ordered wall of bricks. It's way more stable with fewer weak points, which is why it reacts so much slower. All right, now let's meet the other 20% of the team, the aluminates. If the silicates are the brawn of this whole operation, the aluminates are the spark. They're the ones that get the whole reaction started. And the leader of this crew is C3A. This stuff is just pure, raw energy. It reacts almost instantly with water, and when it does, it releases a tremendous amount of heat. It is the catalyst for the entire process. It's the one that screams, "Go!" But wait a minute, hold on. We just established a rule, right? Disordered, messy structures are more reactive. Well, check this out. C3A has a highly ordered, perfectly cubic crystal structure. So how on earth can it be the most reactive compound of them all? This completely breaks our rule. And here is the plot twist. For C3A, a totally different property wins out: solubility. Its tiny little crystals are so soluble, they basically dissolve the second water touches them. And this super fast dissolving just lets the reaction kick off with incredible speed, completely overpowering the fact that it has a tidy, ordered structure. The other aluminate, C4AF, is the total opposite. It's got iron in it, which makes it highly insoluble. Think of it like a hard rock that's just really, really slow to dissolve. And because it doesn't break down easily, it's actually one of the least reactive compounds in the whole mix. Okay, so we've seen two big principles at play here: crystal structure and solubility. Now let's just dig a little deeper into the main rule that really governs how these compounds behave. First, a key term you gotta know: polymorphs. It sounds super fancy, but it's a really simple idea. It just means that the same chemical compound can exist in different crystal forms.
It's kind of like having the exact same set of Lego bricks, but arranging them in different shapes. And that difference in form, it's everything. And this, right here, this is the fundamental rule. All things being equal, chaos leads to action. A more disordered, irregular crystal structure creates a more reactive compound. This one principle perfectly explains the difference in speed between our C3S sprinter and our C2S marathon runner. This chart just visualizes that reactivity perfectly. See, heat of hydration is a direct measure of how fast and how intensely these guys react. I mean, just look at C3A. It is completely off the charts, releasing this massive burst of heat. Then you've got C3S, our sprinter, still running pretty hot, and way, way down at the bottom is C2S, the marathon runner, with the lowest heat release, showing its slow and steady nature. So we've met the team, we've learned the rules of their little microscopic world. But why does any of this chemistry matter in our world, the big world we live in? Oh, it matters immensely. That lightning-fast reaction of C3S, that's the reason a skyscraper's frame can be built in days, not months. The slow, steady strength gain from C2S, that's why a massive dam actually gets stronger and stronger over its entire life. In C3A is so reactive that we have to add another material, gypsum, just to slow it down. If we didn't, concrete would harden in the truck before it ever even got to the job site. So here they are, our 4 superstars one last time. The sprinter for that crucial early strength, the marathon runner for long-term durability, the catalyst that kicks the whole thing off, and the stabilizer that helps form the final solid matrix. Together, this team creates the single most widely used building material in all of human history. It's just an amazing testament to the power of chemistry. So really, the next time you walk past a concrete building, just for a second, remember that elegant dance happening between these 4 compounds, that invisible team working tirelessly inside, holding our modern world together. It's a pretty powerful reminder that inside the most ordinary materials, there's often an incredible, invisible world of science at work.